Hello everyone, let's continue with elementary number theory. Today we'll study linear Diophantine equations. First of all, let me introduce what is a linear Diophantine equation. A Diophantine equation is a polynomial equation with two or more unknowns. In which only integer solutions are allowed. Let me show you an example. An example looks like this. Equation a1s1 plus a2x2 plus ansn equal to b. This is a polynomial equation with n unknowns, n1, x1, x2, xn. This is a polynomial equation with n unknowns. And this equation is linear. This equation is linear because for all unknown, for all variable, the degree is 1. It's called linear equation. This is a Diophantine equation. It's linear. That's why it's called linear Diophantine equation. This is a Diophantine equation. It has n unknowns. It's a polynomial equation with n unknowns. And for all variables, for all unknowns, the degree is 1. It's called a linear equation. Together, it's called a linear Diophantine equation. Now, how do we solve this linear Diophantine equation? How do we solve it? To solve a linear Diophantine equation, there are 3 cases. In order to solve a linear Diophantine equation, there are 3 cases. Case 1. If the GCD of all the coefficients a1, a2, an, if the GCD of all coefficients is 1, then it always has solution. It always has solution. If the GCD of all coefficients a1, a2 up to an, if the GCD is 1, then it always has integer solutions. For Diophantine equation, we only consider integer solutions. Case 2. If the GCD of a1, a2, an equal to d, which is not 1, and d divides b, Then we can divide both sides of an equation by d. Divide both sides of an equation by d. We have a1 over d x1 plus a2 over d x2 plus an over d xn equal to b over d. Since d is the common divisor of a1, a2, an, then those are integers. This is integer, this is integer, this is integer. And since b divides d, this is also integer. That's another Diophantine equation. That's another Diophantine equation. And based on a lemma we did last class, we know that. Let me recall a lemma we did last class. If the GCD of AB is D, then the GCD of A over D comma B over D must be 1. If D is the greatest common divisor of A and B, then when I divide both numbers by D, their greatest common divisor must be 1. Similarly, if there are n integers, the same argument works. The proof is very similar. Similarly, if GCD of n integers, a1, a2, an is D, then when I divide each number by D, their GCD must be 1. The proof is very similar. If the GCD of n integers, a1, a2 up to an is D, then when I divide every integer by D, their greatest common divisor must be 1. Here, since the GCD of a1, a2, an is D, then when I divide each integer by D, their greatest common divisor must be 1. So, for this equation, for this linear Diophantine equation, if I divide both sides by D, I get this. And according to the lemma from last class, we know that the GCD of all coefficients, a1 over D, a2 over D, an over D is 1. According to the lemma we did last class, in this Diophantine equation here, in this new equation here, the GCD of the coefficients a1 over D, a2 over D, an over D must be 1. Then this new equation is satisfies the condition of case 1. So in the second case, if the GCD of the coefficients is D, which is not 1, and D divides B, then I can divide both sides of the equation by D. We get a new equation. This new equation satisfies all conditions in case 1. We can solve it in the same way as in case 1. That's case 2. Case 3. If the GCD of a1, a2, an is D, which is not 1, and D doesn't divide B. If the GCD of a1, a2, an is D, which is not 1, and D doesn't divide B, then there are no solutions. There are no integer solutions. Then there are no integer solutions. In case 3, how do we know there are no integer solutions? Let's prove the following lemma. Let A1, A2, AN, and B be integers. If GCD of A1, A2, AN is D, and D doesn't divide B, then the Diophantine equation the linear Diophantine equation A1x1 plus A2x2 plus ANSN equal to B has no integer solutions. Let's prove it. Prove by contradiction. Let's prove by contradiction. To show an equation has no solution directly is not easy. So we try to prove by contradiction. Assume this equation A1S1 plus A2S2 plus ANSN equal to B. Assume it has integer solutions. Then there exist integers S1, S2 up to Sn such that A1S1 plus A2S2 plus ANSN equal to B, because all these integers satisfy this equation. S1, S2, Sn satisfy this equation. So we have A1, S1 plus A2, S2 plus ANSN equal to B. Since D is the greatest common divisor of A1, A2, and AN, then since D is the greatest common divisor, then D is a divisor, then D divides A1, D divides A2, and D divides AN. Hence, if D divides every A1, A2, AN, then D divides any linear combination of A1, A2, AN with integer coefficients. Hence, D divides any linear combination of A1, A2, AN with integer coefficients. That means D divides A1S1 plus A2S2 plus ANSN. That's a linear combination of a1, a2, an with integer coefficients because s1, s2, sn, they are integers with integer coefficients. That's a linear combination of a1, a2, an with integer coefficients. Hence, D divides B because this number a1, a2 plus a1, s1 plus a2, s2 plus an, sn, this number equal to B. So D divides B. That's a contradiction. Assumption says D doesn't divide B. This is a contradiction because the assumption says D doesn't divide B. It's a contradiction. It's a contradiction, so that means our assumption must be wrong. That means this linear Diophantine equation has no integer solutions. So the linear Diophantine equation a1 s1 plus a2 s2 plus an sn equal to B has no integer solutions. Let's complete the proof of this lemma. So in case 3, if the GCD of a1, a2, an is D, which is not 1, and D doesn't divide B, then there are no integer solutions. This linear Diophantine equation has no integer solutions. Next, let's look at some examples. Solve each of the following linear Diophantine equations. We know that in general, a linear Diophantine equation has 2 or more unknowns. Let's look at the simplest case first. In the simplest case, a linear Diophantine equation has only 2 unknowns. So in the simplest case, a linear Diophantine equation has only 2 unknowns. Consider this equation. 9x plus 17y equal to 7. This is a linear Diophantine equation which contains only 2 unknowns, x and y. It has only 2 unknowns, x and y. In order to solve for x and y, let's first of all verify the coefficients of x and y. Let's first of all verify the coefficients of the unknowns. So verify the coefficient on the left side. The GCD of 9 and 17 only take GCD from the coefficient on the left side. The GCD of 9 and 17 is 1. So according to case 1, since GCD of 9 and 17 is 1, according to case 1, this equation has integer solutions. This equation has integer solutions. So let's solve it. So let me first of all rewrite the equation first. In order to solve for x and y, let me first of all rewrite the equation first. So rewrite the equation. First step, try to isolate the term with smaller coefficient. Isolate the term with smaller coefficient. Either one is okay, but to make it easier, isolate the term with smaller coefficient. Either one is okay, but either term is okay. Let me isolate, to make it easier, let me isolate the term with smaller coefficients. So get 9x by itself. Since we know there is solution for x and y, this x must be integer. Since we know that there is integer solution for x and y, this x is an integer. If 9 times the integer equal to this number, that means 9 divides 7 minus 17y. If 9 times the integer equal to this number, that means 9 divides this number. 9 divides this number. Then, by definition of linear congruence, this statement can be written as 7 congruent to 17y mod 9. This statement can be written as 7 congruent to 17y mod 9. And we know that for any linear congruence, A is congruent to B mod M. That's equivalent to say B is congruent to A mod M. For any linear congruence, I can switch left side and right side. So here I can switch left side and right side. Write it as 17y congruent to 7 mod 9. 17y congruent to 7 mod 9. So first step, rewrite this equation as 17y congruent to 7 mod 9. Rewrite this equation as 17y congruent to 7 mod 9. 17y congruent to 7 mod 9. Then solve this linear congruence. 17 is more than 9. So first of all, take a remainder. 17 divided by 9, remainder is A. Okay, AY congruent to 7 mod 9. Next, in order to solve for y, I try to find the inverse of A mod 9. Can we find some integer times A plus some integer times 9 equal to 1? Can we find some integer times A plus some integer times 9 equal to 1? We can use -1 and 1 here. So we know that number in front of A is the inverse of A. Inverse of A here congruent to -1 mod 9. Inverse of A congruent to -1 mod 9. And we try to use the least non-negative residue at 9 here. Inverse of A congruent to A mod 9. Inverse of A congruent to A mod 9. Then I can multiply inverse of A to both sides of this congruence. Inverse of A congruent to A mod 9. So on the left side we get y by itself. Y congruent to 56 mod 9. Then take 56 divided by 9, take remainder. Take 56 divided by 9, take remainder. 56 divided by 9, remainder is 2. So y congruent to 2 mod 9. Write it as an equation. That means y equal to 2 plus 9t. Write it as an equation. That means y equal to 2 plus 9t, where t is an integer. Y equal to 2 plus 9t, where t is an integer. Then once I know y, plugging y here, I can solve for x. Once I know y, plugging y here, I can solve for x. So 9x plus 17 times y equal to 7. 9x plus 17 times y equal to 7. Then solve for x. Distribute 17, we get 34 plus 17 times 9 is 153 times t equal to 7. Then solve the equation for x. We have 9x equal to -27 minus 153t. Then divide both sides by 9. If we solve everything correctly, we must get integer solutions. If we don't get integer solution, that means we make mistakes somewhere. If we solve correctly, we must get integer solutions here. 27 divided by 9 is 3. 153 divided by 9 is 17. So x is -3 minus 17t. So the solution for x and y, put it together. X is -3 minus 17t. Y is 2 plus 9t, where t can be any integer. That's the solution to this linear Diophantine equation. Next example, 23 plus 15y equal to 35. This is a linear Diophantine equation of two unknowns, x and y. We try to find integer solutions for x and y. First step, let's verify the GCD for the coefficients. GCD of 23 and 15 is 1. The according to case 1, it has integer solutions. Let's solve it. So, first step, I try to write the term with smaller coefficient in the front. First step, to make it easier, I try to write the term with smaller coefficient in the front. So this equation can be rewritten as 15y plus 23x equal to 35. To make it easier, I try to write a term with smaller coefficient in the front. Next, rewrite this equation as a linear congruence. Next, rewrite this equation as a linear congruence. This equation can be rewritten as 23x congruent to 35 mod 15. This equation can be rewritten as 23x congruent to 35 mod 15. The detail is in this equation, if I move 23x over, I have 15y equal to 35 minus 23x. Since 15 times the integer equal to this number, that means 15 divides 35 minus 23x. Then by the definition of congruence, this statement can be written as 35 congruent to 23x mod 15. Then I can switch left side and right side. 23x congruent to 35. Mod 15. So that's exactly what we have here. 23x congruent to 35 mod 15. So the shortcut is 23x congruent to 35 mod 15. 23x congruent to 35 mod 15. In general, write a smaller term in the front. Write a term with smaller coefficient in the front, make it a little easier. Write a term with smaller coefficient in the front. Then write it as a linear congruence. 23x congruent to 35 mod 15. Then solve this linear congruence for x. Here, 23 is more than 15. I can take 23 divided by 15 and take the remainder. 23 divided by 15, the remainder is a. So 23x is congruent to ax. On the right side, 35 is also more than 15. So I can take 35 divided by 15, take the remainder. 35 divided by 15, take the remainder. I get 5. Next, I try to find the inverse of a mod 15. Next, I try to find the inverse of a mod 15. I try to find some integer times a plus some integer times 15 equal to 1. Here, for small number, we can try. We know that 2 times a plus negative 1 times 15 is 1. The number in front of a is the inverse of a. So inverse of a congruent to 2 mod 15. So I can multiply both sides by inverse of a. Here I can multiply both sides by inverse of a. Inverse of a congruent to 2 mod 15. If I multiply both sides by inverse of a, on the left side I get s by itself. On the right side, 5 times 2 is 10. And this 10 is less than 15. So this is the least non-negative residue. That's okay. Next, write this congruence as an equation. Write this congruence as an equation. I can write this as x equal to 10 plus 15t, where t is an integer. S equal to 10 plus 15t, where t is an integer. Then I can plug in x, solve for y. I can plug in x, solve for y. 15y plus 23x, x is 10 plus 15t. 15y plus 23x, x is 10 plus 15t, equal to 35. Then solve an equation for y. 23 times 10 is 230. 23 times 15, I don't know what it is. Let me leave it the way it is. Equal to 35. Then we try to solve the equation for y. Let's isolate 15y first. 15y equal to negative 195 minus 23 times 15t. Then in order to get y by itself, I divide both sides by 15. (195) divided by 15 is 13. Negative 195 divided by 15 is negative 13. And 23 times 15 divided by 15 is 23. So if we solve correctly, we must get integer solutions for both numbers. If we solve correctly, both numbers must be integers. So that's y, that's x, that's y. The final answer, write s and y together. S is 10 plus 15t. Y is negative 13 minus 23t, where t is an integer. That's the solution to this linear Diophantine equation. That's the solution to this linear Diophantine equation. Next example, 13x minus 5y equal to 7. 13x minus 5y equal to 7. So first step, let's verify the GCD for the coefficient on the left side. GCD of 13 and 5. When we verify GCD, it doesn't matter it's positive or negative. We only use positive number here. For GCD, we only use positive number. It doesn't matter it's positive or negative. We only use the positive numbers, positive 13 and positive 5 here. GCD of 13 and 5 is 1. Then according to case 1, we know that it has integer solutions for x and y. Next, try to write the smaller term, the term with smaller coefficient in the front. Try to write the term with smaller coefficient in the front. To make it easier, write the term with smaller coefficient in the front. Negative 5y plus 13x equal to 7. Next, try to write it as a linear congruence. Try to write this equation as a linear congruence. This equation can be written as 13x congruent to 7 mod positive 5. 13x congruent to 7 mod positive 5. The reason is negative 5y plus 13x equal to 7. Let me first of all isolate 5y. I have negative 5y equal to 7 minus 13x. Then negative 5y can be written as 5 times negative y. If there is integer solution for x and y must be integer. If y is integer, negative y is also integer. If 5 times integer equal to this number, that means 5 divides this number. So 7 congruent to 13x mod 5. By the definition of linear congruence, 7 congruent to 13x mod 5. Then I can switch left side and right side. 13x congruent to 7 mod 5. So that's how I rewrite this equation as a linear congruence. 13x congruent to 7, 13x congruent to 7 mod positive 5. 13x congruent to 7 mod positive 5. Now let's solve this linear congruence for x. 13 is more than 5, so I can take 13 divided by 5, take remainder. 13 divided by 5, remainder is 3. So 13x is congruent to 3x. 7 is more than 5, so I can take 7 divided by 5, take remainder. 7 divided by 5, remainder is 2. Next, we try to find inverse of 3 mod 5. Can we find some number times 3 plus some number times 5 equal to 1? For small numbers, we can try it out. We know that 2 times 3 plus negative 1 times 5 is 1. So inverse of 3 is a number in front of 3. Inverse of 3 congruent to 2 mod 5. Then multiply both sides by inverse of 3. Inverse of 3 congruent to 2 mod 5. Then when we multiply, on the left side we get x. On the right side, 2 times 2 is 4. So we have x congruent to 4 mod 5. That means s equal to 4 plus 5t, where t is the integer. Then we can plug in x, solve for y. Then we can plug in x, solve for y. Negative 5y plus 13 times x. X is 4 plus 5t, equal to 7. Distribute 13, we get 52 plus 65t, equal to 7. Then solve for y. Let me move this 2 term over. Negative 5y equal to negative 45 minus 65t. Then divide both sides by negative 5. Y equal to 9 plus 13t. If we solve correctly, all these numbers must be integer. If we solve correctly, all these numbers must be integers. If we don't get integer here, that means we made mistake somewhere. We need to go back and check our work. So if we solve it correctly, these both numbers must be integers here. So that's the solution for x and y. X is 4 plus 5t. Y is 9 plus 13t, where t can be any integers. That's the solution to this linear Diophantine equation. Next example, 32x plus 50y equal to 72. We try to find integer solutions for x and y. First step, let's find the GCD from the coefficients on the left side. GCD of 32 and 50 is 2, which is not 1 here. GCD is 2, so let's try to verify. That's 2 divides 72. If 2 divides 72, then I can divide every numbers by 2. I can divide both sides by 2 and get a new equation. If 2 doesn't divide 72, then by case 3, there's no integer solutions. If 2 doesn't divide 72, then by case 3, there's no integer solutions. Now let's check. That's 2 divides 72. We know that 2 times 36 is 72. So 2 divides 72. That's good. Since 2 divides 72, I can divide both sides by 2 and get a new equation. I can divide both sides by 2 and get a new equation. So I have 16 plus 25y equal to 36. I divide both sides by 2, get a new equation here. Then try to write this equation as a linear congruence. Try to rewrite this equation as a linear congruence. 25y congruent to 36 mod 16. 25y congruent to 36 mod 16. Rewrite this equation as a linear congruence. 25y congruent to 36 mod 16. Then solve for y. Solve this linear congruence for y. 26 is more than 16, so I can take a remainder. So 25 is more than 16, so I can take a remainder. 25 divided by 16, remainder is 9. 36 is also more than 16, I can take a remainder. 36 divided by 16, 36 divided by 16, remainder is 4. Mod 16. Next, try to find inverse of 9 mod 16. Try to find inverse of 9 mod 16. Can we find some integer times 9 plus some integer times 16 equal to 1? If we can guess, we must use the extended Euclidean algorithm. But can we guess? Can we find answer here? We can try. We know 9 times 9 is 81. 5 times 16 is 80. 81 minus 80 is 1. So I put minus 5 here. 9 times 9 is 81. Minus 80 is 1. So since I can find integers 9 and negative 5 here, the number in front of 9 is the inverse of 9. So inverse of 9 congruent to 9 mod 16. Then I can multiply both sides by inverse of 9. I can multiply both sides by inverse of 9. Inverse of 9 congruent to 9 mod 16. Then multiply left side and right side. 9 times inverse of 9 get cancelled. I get y by itself. on the right side, 4 times 9 is 36, minus 16. Since 36 is more than 16, I take 36 divided by 16 and take remainder. 36 divided by 16, remainder is 4. So y congruent to 4 minus 16. Then write y as an equation. Y equal to 4 plus 16t, where t is an integer. Then I can plug in y and solve for x. Plug in y, solve for x. 16x plus 25y. Y is 4 plus 16t equal to 36. Then distribute 25. I get 16x plus 100 plus 25 times 16 is 400 t equal to 36. Then 16x equal to negative 64 minus 400t. Then I can divide both sides by 16. If we solve correctly, we must get integers on the right side. Negative 4 minus 25t. If we don't get integer here, we must go back and check the work. That means we made mistake somewhere. So that's the solution for x and y. X is negative 4 minus 25t. Y is 4 plus 16t. That's the solution to this linear Diophantine equation. So, if the GCD is not 1, we must check. If the GCD divides the constant on the right side, then that's case 2. I divide every number by the GCD. If the GCD doesn't divide the number on the right side, that's case 3. According to case 3, there are no integer solutions. If the GCD doesn't divide the number on the right side, there are no integer solutions. Next example, negative 48x plus 39y equal to 27. We try to find integer solutions for x and y. First step, let's verify the GCD for the coefficients on the left side. GCD of 48 and 39. So when we find GCD, we only use positive numbers. We only use positive 48 and positive 39. GCD of positive 48 and positive 39 is 3, which is not 1. Then let's check. If does 3 divides the number on the right side? Let's check. Does 3 divides the number on the right side? If 3 divides the number on the right side, then I can divide both sides of an equation by 3 and get a new equation, and then solve the new equation. But if 3 doesn't divide on the right side, if 3 doesn't divide the number on the right side, then according to case 3, there are no integer solutions. Let's check. Does 3 divide 27? We know that 3 times 9 is 27. So yes, 3 divides 27. 3 divides 27. Then I can divide both sides by 3 and get a new equation. I can divide both sides by 3 and get a new equation. If I divide both sides by 3, I get negative 16x plus 13y equal to 9. That's a new equation. Then to make it easier, I put a term with smaller coefficient in the front. We consider 13 is less than, ignore the sign. We consider 13 is less than 16. Ignore this negative sign. We consider 13 is less than 16. So put a term with smaller coefficient in the front. Right, 13y plus negative 16x equal to 9. Write the term with smaller coefficient in the front. Consider 13 is less than 16. Don't use this sign here. Consider 13 is less than 16. So put 13y in the front. So write the term with smaller coefficient in the front. 13y plus negative 16x equal to 9. Then rewrite this equation as a linear congruence. This equation can be rewritten as negative 16x congruent to 9 minus 13. This equation can be rewritten as negative 16x congruent to 9 minus 13. Then, since 16 is more than 13, we can take 16 divided by 13 and take remainder. 16 divided by 13, remainder is 3. So for negative 16, remainder is negative 3. Negative 16 congruent to negative 3. 16 divided by 3, remainder is 3. 16 divided by 13, remainder is 3. So negative 16 congruent to negative 3. Negative 16x congruent to negative 3x. 9 is less than 13, so I can leave it the way it is. In general, we try to use positive number here. Negative 3 plus 13 is 10. So negative 3x congruent to 10x. So 10x congruent to 9 minus 13. Next, we try to find inverse of 10 minus 13. Can we find some integers times 10 plus some integers times 13 equal to 1? We know that 4 times 10 is 40. 3 times 13 is 39. 40 minus 39 is 1. So I can put negative 3 here. 40 minus 39 is 1. So the number in front of 10 is the inverse of 10. Inverse of 10 is 4 minus 13. Inverse of 10 congruent to 4 minus 13. Then multiply both sides by inverse of 10. Inverse of 10 congruent to 4 minus 13. Then multiply left side to the left side, right side to the right side. S congruent to 36 minus 13. Then since 36 is more than 13, I can take 36 divided by 13 and take remainder. 36 divided by 13, remainder is 10. Then write this congruence as an equation. It can be written as x equal to 10 plus 13t, where t is an integer. Then substitute x here, solve for y. Substitute x here, solve for y. Once we know x, I can substitute x here, solve for y. 13y minus 16x, x is 10 plus 13t. Equal to 9. Substitute x here, solve for y. I have 13y minus 160 minus 16 times 13. I don't know what it is. Let me leave it the way it is. Equal to 9. Then solve the equation for y. I have 13y equal to 169 plus 16 times 13t. Then I can divide both sides by 13. If I divide both sides by 13, 169 divided by 13 is 13. 16 times 13t divided by 13 is 16t. If we solve everything correctly, we must get integers for both. For both numbers, we must get integers here. Then that's the solution to this linear Diophantine equation. So x is 10 plus 13t. Y is 13 plus 16t, where t is an integer. That's the solution to this linear Diophantine equation. Next, 12x plus 30y equal to 39. Solve this linear Diophantine equation for x and y. First step, let's find GCD for the coefficients on the left side. GCD of 12 and 30. GCD of 12 and 30 is 6. Now let's check. Does 6 divide the number on the right side? If 6 divides the number on the right side, I can divide both sides by 6. But if 6 doesn't divide the number on the right side, then according to case 3, there are no integer solutions for s and y. So here, let's check. Does 6 divide 39? We know 39 divided by 6 is not integer. 39 divided by 6 is not integer. That means 6 doesn't divide 39. 6 doesn't divide 39. 6 doesn't divide 39. Then, according to case 3, there are no integer solutions. There are no integer solutions. Next example, 6x plus 10y plus 15z equal to a. This is a linear Diophantine equation with 3 unknowns, s, y, and z. We try to find their integer solutions. So, first step, find GCD from the coefficients on the left side. GCD of 6, 10, and 15. GCD of 6, 10, and 15 is 1. Then we know that we have integer solutions for s, y, and z. How do we find integer solutions for s, y, and z? First step, I set 6x plus 10y equal to w. Here, the GCD of 6 and 10 is 2. In order to guarantee this equation has a solution, I must set 6x plus 10y equal to 2w. The GCD of 6 and 10 is 2. In order to guarantee this equation has a solution, it must equal to a multiple of 2. So I set this equal to 2w. So set 6x plus 10y equal to 2w. Then the equation can be rewritten as, then we have 2w plus 15z equal to a. Then we have 2w plus 15z equal to a. Now I can solve for w and z. Once I know w, I can plug in w here, solve for x and y. In this equation here, I can solve for w and z. Once I know w, I can plug in w here, solve for x and y. So let me solve this equation for w first. Once I know w, plug in w here, solve for x and y. So let me rewrite this equation as a linear congruence first. I have 15z congruent to a mod 2. 15z congruent to a mod 2. Since 15 is more than 2, I take 15 divided by 2, take the remainder. Since 15 is more than 2, I take 15 divided by 2 and take the remainder. 15 divided by 2, the remainder is 1. So I get 1z here. A divided by 2, remainder is 0. A is more than 2, so I take a divided by 2. A divided by 2, remainder is 0. Then 1z is the same as z. Z congruent to 0 mod 2. Write this as an equation. Z equal to 2t. Z equal to 0 plus 2t. Z equal to 0 plus 2t, where t is an integer. That's the same as saying z equal to 2t. Once I know z, I can plug in here, solve for w. So I get 2w plus 15z, z is 2t, equal to a. Then I have 2w plus 30t equal to a. 2w equal to a minus 30t. 2w equal to a minus 30t, then divide both sides by 2. W equal to 4 minus 15t. Now I know w. I can solve this for x and y. Now I know w here. I can solve this equation for x and y. 6x plus 10y equal to 2w. GCD of 6 and 10 is 2, and 2 divides 2w, so I can divide both sides by 2. GCD of 6 and 10 is 2, and 2 divides 2w, so I can divide both sides by 2 and get a new equation. I have 3x plus 5y equal to w. Then rewrite this as a linear congruence. I have 5y congruent to w mod 3, 5y congruent to w mod 3. And plugging w is 4 minus 15t. Plugging w here. W is 4 minus 15t. So I get 5y congruent to 4 minus 15t mod 3. Five is more than 3, so I can take 5 divided by 3, take the remainder. 5 divided by 3, remainder is 2. I get 2y here. 4 is more than 3, so I can take 4 divided by 3, take the remainder. 4 divided by 3, remainder is 1. Next, I take 15 divided by 3, take the remainder. 15 divided by 3, remainder is 0. 0 times t is 0. Mod 3. Then I have 2y congruent to 1 minus 0 is 1. 2y congruent to 1 mod 3. Then we try to find inverse of 2 mod 3. For small numbers, we can try. Can we find some integer times 2 plus some integer times 3 that equal to 1? For small numbers, we can try. We know that 2 times 2 is 4. And negative 1 times 3 is negative 3. 4 minus 3 is 1. So the number in front of 2 is the inverse of 2. Inverse of 2 congruent to 2 mod 3. Inverse of 2 congruent to 2 mod 3. Then multiply both sides by inverse of 2. Then if I multiply, 2 and negative 2 will cancel, we get y by itself. 1 times 2 is 2 mod 3. So y equal to 2 plus 3, don't use the same letter, use a different letter here. Use a different letter, don't use t. We use t already, use a different letter. Y equal to 2 plus 3 times s, where s is an integer. Once I know y, I can plug in y here. I know w, I know y, I can plug in y and w, solve for x. Plug in y and w, solve for x. So I have 3x plus 5y y is 2 plus 3s equal to w. W is 4 minus 15t. Then solve an equation for x. I have 3x plus 10 plus 15s equal to 4 minus 15t. Then 3x equal to negative 6. 10 minus 4 is negative 4 plus negative 10 is negative 6 minus 15t minus 15s. Then divide both sides by 3. S equal to negative 2 minus 5t minus 5s. If we solve everything correctly, we must get integers everywhere. So that's x, that's y, that's z. So the final answer, x equal to negative 2 minus 5t minus 5s y equal to 2 plus 3s, g equal to 2t, s equal to negative 2 minus 5t minus 5s, y equal to 2 plus 3s, g equal to 2t, where s and t can be any integers. That's the solution to this linear Diophantine equation. Next example, 96x plus 56y minus 126z equal to 100. We try to find integer solutions for x, y, and z. So first step, find GCD of the coefficient on the left side. Find GCD of the coefficients on the left side. Find GCD of 96, 56, and 126. If the number is negative, drop negative sign. Put positive 26. Put positive 126 here. Then find the GCD. Let's use prime factorization to find the GCD. 96 can be factored as 6 times 16. 6 can be factored as 2 times 3. 16 can be factored as 4 times 4. 4 can be factored as 2 times 2. 2 times 2. So 96 is 2 to the power 5 times 3 to the power 1. 56 is 7 times a. 7 is a prime. A is 4 times 2. 4 is 2 times 2. So 56, the prime factorization is 2 to the power 3 times 7 to the power 1. 126 can be factored as 6 times 21. 6 is 2 times 3. 21 is 3 times 7. So the prime factorization for 126 is 2 to the power 1 times 3 to the power of 2 times 7 to the power of 1. Then let's write this number together. 96 is 2 to the power 5 times 3 to the power 1. If there's no 7, write 7 to the power 0. That's 96. 56, we have 2 to the power 3. If there's no 3, write 3 to the power of 0. 7 to the power of 1. 126 is 2 to the power of 1. 3 to the power of 2. 7 to the power of 1. Then for the GCD, choose the lowest power for each prime number. Choose the lowest power. 2 to the power of 1. 3 to the power of 0. 7 to the power of 0. Together is 2. So the GCD is 2. Now check. Does 2 divide 100? Does 2 divide the number on the right side? We know 2 times 50 is 100. 2 times 50 is 100. So 2 divides 100. That's true. 2 divides 100. That's true. If 2 divides 100, then divide every number by 2. Divide both sides by 2. Divide both sides of an equation by 2. I have 48x plus 28y minus 63z equal to 50. If 2 doesn't divide this number, there are no integer solutions, period. If 2 doesn't divide 100, there are no integer solutions, period. But if 2 divides 100, we divide both sides of the equation by 2. And we get a new equation. That's a new equation we have. That's a new equation. Now solve this new equation. First step, put the coefficient in orders. Write the term with smaller coefficient first. Put the coefficient in orders. Write the term with smaller coefficient. Write the term with smaller coefficient first. We have 28y plus 48x. Put the coefficient in orders. Write the term with smaller coefficient first. When we compare the coefficient, don't use the sign, just compare the numbers. 48, 28, and 63. Don't say negative 3 is smaller. Negative 63, we only use the number 63. 28, 48, 63. Put in order. Smaller number come first. Don't use the sign. Don't carry the sign. When you compare the number, don't use the sign. Just compare 48, 28, and 63. 63 is the largest, 28 is the smallest, 48 is the second largest. So put in order. Put the terms in order. The term with smaller coefficient comes first. Next, set these two the first two terms equal to W. But here, for 28 and 48, the GCD is 4. For 28 and 48 here, the GCD is 4. In order to guarantee this equation has a solution, we must make this number W to be a multiple of 4. So let's make 4W. The GCD of 28 and 48 is 4. In order to guarantee this equation has a solution, I need to make it 4W. So set 28y plus 48x equal to 4W. In order to guarantee this equation has a solution, this number must be a multiple of the GCD. The GCD here is 4, so it must be 4W. If I set these two terms equal to 4W, then we have (4W minus 63z) equal to 50. (4W minus 63z) equal to 50. Next, we try to solve this equation first. Solve this equation for W and Z first. Then plug in W, solve for X and Y. So, in order to solve this equation, let's first of all rewrite this equation as a linear congruence first. Let's rewrite this equation as a linear congruence first. So, rewrite this as a linear congruence. Negative 63z congruent to 50 mod 4. Don't forget negative sign. We must carry negative sign. Negative 63z congruent to 50 mod 4. Negative 63 congruent to 50 mod 4. Then let's simplify. Negative 63 is more than 4. So we take negative 63 divided by 4, take the remainder. Let's take 63, ignore negative sign. Temporarily ignore negative sign. Take 63 divided by 4, take the remainder. 63 divided by 4, remainder is 3. So negative 63 will congruent to negative 3. If I take 63 divided by 4, remainder is positive 3. Then negative 63 congruent to negative 3. Negative 63z congruent to negative 3z. And also, 50 is more than 4. So I can take 50 divided by 4 and take the remainder. 50 divided by 4. 50 divided by 4, remainder is 2. Then, since we don't want negative number here, so I can add 4 to make it positive. We don't want negative number here. Add 4 to make it positive. If I add 4z here, if I add 4 here, negative 3 plus 4 is 1. So negative 3z congruent to 1z. We don't want negative number here, so I can add 4 to negative 3. Negative 3 plus 4 is 1. So negative 3z congruent to 1z. We have 1z congruent to 2 mod 4. Then we know that 1z is the same as z. So z congruent to 4 mod z congruent to 2 mod 4. That means z equal to 2t plus 4. Z equal to 2 plus 4t. Z equal to 2 plus 4t, where t is an integer. Once I know z here, I can plug in to find w. Once I know z, I can plug in to find w. 4w minus 63z. Z is 2 plus 4t equal to 50. Then distribute 63. We have 4w minus 126 minus 252t equal to 50. Then solve for w. 4w minus 4W equal to 176 plus 252t. Then divide both sides by 4. 176 divided by 4, that's 44 plus 252 divided by 4, that's 63t. If we solve correctly, we must get integer here. We must get both integers here. If we don't get integer here, that means we made mistake somewhere. We must go back and check the work. So let's W. Once I know W, I can solve for x and y. Once I know W, I can solve for x and y. Now, this equation is 28y plus 48x equal to 4w. Here I can, GCD of 28 and 48 is 4. And 4 divides 4w, so I can divide both sides by 4. GCD of 28 and 48 is 4. And 4 divides 4w, so I can divide both sides by 4. If I divide both sides by 4, I have a new equation. 7y plus 12x equal to w. Then rewrite this as a linear congruence. Rewrite this as a linear congruence. Rewrite this as a linear congruence. I have 12x congruent to w mod 7. 12x congruent to w mod 7. Rewrite this as a linear congruence. 12x congruent to w mod 7. Then I can plug in w. Then plug in w. W is 44 plus 63t. Mod 7. 12 divided by 12 is more than 7, so I take 12 divided by 7. 12 divided by 7, remainder is 5. 44 is more than 7. If I take 44 divided by 7, 44 divided by 7, remainder is 2. If I take 63 divided by 7, 63 divided by 7, remainder is 0. 0 times t is 0. Mod 7. Then I have 5x congruent to 2 mod 7. So 5x congruent to 2 mod 7. Next, I try to find inverse of 5 mod 7. I try to find inverse of 5 mod 7. Can we find some integer times 5 plus some integer times 7 that equal to 1? We can try. We know 3 times 5 is 15. 2 times 7 is 14. 15 minus 14 is 1. So I can put negative 2 here. 3 times 5 plus negative 2 times 7 is 1. 15 minus 14 is 1. Then the number in front of 5 is inverse of 5. The number in front of 5 is inverse of 5. So inverse of 5 congruent to 3 mod 7. Inverse of 5 congruent to 3 mod 7. Multiply both sides by inverse of 5. Multiply both sides by inverse of 5. Inverse of 5 congruent to 3 mod 7. Then multiply inverse of 5 to both sides. On the left side, I get x by itself. On the right side, 2 times 3 is 6. So x congruent to 6 mod 7. X congruent to 6 mod 7. Then write this as an equation. Write this as an equation. I write s equal to 6 plus 7. Use a different letter. We use t already. Use a different letter. S equal to 6 plus 7s, where s is an integer. Then in this equation, we know x, we know w. We can plug in x and w, solve for y. In this equation here, we know x, we know w. We can plug in x and w, solve for y. 7y plus 12 times x, x is 6 plus 7s, equal to w. W is 44 plus 63t. Distribute 12. 12 times 6 is 72. 12 times 7 is 84s. 12 times 7s is 84s, equal to 44 plus 63t. Then 7y equal to 44 minus 72, that's 28, minus 84s plus 63t minus 84s. Then I can divide both sides by 7. Y equal to 4 plus 9t minus 12s. If we solve everything correctly, we must get integer here. 4, 9, negative 12. We must get integer here. If we don't get integer here, that means we made mistake somewhere. If we don't get integer here, that means we made mistake somewhere. We must go back and check our work. So that's a solution for x, y, and z. We have a solution for x, y, and z. They are the solution for this linear Diophantine equation. So the solution here is x equal to 6 plus 7s y equal to 4 plus 9t minus 12s. Z equal to 2 plus 4t, where s and t are integers. That's the solution to this linear Diophantine equation. Next example, 24x plus 36y plus 42z plus 49w equal to 50. This is a linear Diophantine equation with 4 unknowns, x, y, z, w. We are looking for their integer solutions. So first step, find the GCD from the coefficients on the left side. Find GCD for 24, 36, 42, and 49. Here we can use prime factorization. We can use prime factorization to find the GCD. 24 can be factored as 4 times 6. 4 can be factored as 2 times 2. 6 can be factored as 2 times 3. So the prime factorization for 24 is 2 to the power 3 times 3 to the power 1. 36 can be factored as 6 times 6. 6 can be factored as 2 times 2. 2 times 3. So the prime factorization for 36 is 2 squared times 3 squared. 42 can be factored as 6 times 7. 6 can be factored as 2 times 3. 7 is a prime. So the prime factorization for 42 is 2 to the power 1 times 3 to the power 1 times 7 to the power 1. That's the prime factorization for 42. Then for 49, the prime 49 is 7 times 7, so the prime factorization is 7 squared. So we have primes 2, 3, 7. 24 can be written as 2 to the power 3 times 3 to the power 1 times 7 to the power of 0. If 7 is missing, write 7 to the power of 0. 36 is 2 to the power 2 times 3 to the power 2 times 7 to the power of 0. If 7 is missing, write 7 to the power of 0. 42 is 2 to the power 1 times 3 to the power 1 times 7 to the power 1. 49 is, since 2 and 3 they are both missing, write 2 to the power 0, 3 to the power of 0, 7 to the power of 2. Then for GCD, we choose the lowest power for each prime. For number 2, lowest power is 0. For number 3, lowest power is 0. For number 7, lowest power is 0. 2 to the power 0 times 3 to the power of 0 times 7 to the power of 0 is 1. So the GCD of this 4 number is 1. Then we know it has integer solutions. So how do we solve it? First step, put the coefficients in order. Put the coefficients in order. They are in order. Run the terms in order. run the terms in order. Make sure the coefficient is from smaller to larger. Here it is in order. 24, 36, 42, 49. It is in order. Now, if there are four unknowns, we group the first three terms together. If there are four unknowns, if there are 10 unknowns, we group the first nine terms together. If there are four unknowns, we group the first three terms together. So we set (24x plus 36y plus 42z) equal to, if I set it equal to w, there's no guarantee it has solution. This w must be a multiple of their GCTs. For 24, 36, and 42, their GCT is 6. For 24, 36, and 42, their GCT is 6. So in order to guarantee it has a solution, we must set this equal to 6w. Since the GCT of 24, 36, and 42 is 6, in order to guarantee this equation has a solution, we must set this equation equal to 6w. So this must equal to a multiple of 6. Set this equal to 6w. Then we have, don't use w, we have w already. Use a different letter. Use a different letter here. Let's call 6u. Let's call this 6u. Don't use the same letter again. Let's call this 6u. Then we have 6u plus 49w equal to 50. I set the first return equal to 6u. So this equation can be rewritten as 6u plus 49w equal to 50. Then solve this linear congruence. Solve these equations. First of all, rewrite this equation as a linear congruence first. Then we can find u and w. Once I find u, I can plug in u here. Solve for s, y, and z. So let's rewrite this equation as a linear congruence first. I have 49w congruent to 50 mass 6. 49w congruent to 50 mass 6. Since 49 is more than 6, I can take 49 divided by 6 for the remainder. 49 divided by 6, the remainder is 1. So 49w is congruent to 1w. Take 50 divided by 6, take the remainder. 50 divided by 6, remainder is 2. Then 1w is the same as w. W congruent to 2 mass 6. So w equal to 2 plus 6t. W equal to 2 plus 6t. Where t is an integer. Next, once I know w, I can plug in w here, solve for u. Once I know w, I can plug in w here, solve for u. 6u plus 49w, w is 2 plus 6t, equal to 50. Distribute 49, I get 6u plus 98 plus 49 times 6, I don't know what it is, let me leave it the way it is. 49 times 6t, equal to 50. Then solve for u. 6u equal to negative 48 minus 49 times 6t. Then divide both sides by 6. Divide both sides by 6. Negative 48 divided by 6 is negative 8. Negative 49 times 6t divided by 6 is negative 49t. That's u. Then once I know u, plug in u here. Solve the equation for s, y, z. Once I know u, plug in u here. Solve the equation for s, y, z. So here we have 24x plus 36y plus 42z equal to 6u. This is a linear Diophantine equation with three unknowns. Since we know it already, this is a linear Diophantine equation with three unknowns, S, Y, and Z. Now, first of all, the GCD of 24, 36, and 42 is 6. And we know that 6 divides 6u, so I can divide both sides by 6. The GCD of 24, 36, and 42 is 6. And 6 divides 6u, so I can divide both sides by 6. If I divide both sides by 6, I have a new equation. 4x plus 6y plus 7z equal to u. Then solve this equation for s, y, z. In order to solve a linear Diophantine equation with three unknowns, I set the first two terms, I group the first two terms together. Set the first two terms equal to v. In order to get, but the GCD for 6 and 4 is 2. GCD for 4 and 6 is 2. In order to guarantee this equation has a solution, it must be a multiple of 2. I must set this two term equal to a multiple of 2. So I set 4x plus 6y equal to 2v. Set 4x plus 6y equal to 2v. In order to guarantee this equation has a solution, I must set this equal to a multiple of the GCD. The GCD of 4 and 6 is 2. So I must set this equal to a multiple of 2. So let's call this 2v. If I set 4x plus 6y equal to 2v, I have then we have two v plus 7z. 2v plus 7z equal to u. In this equation, we know u already, so I can solve for v and z. We know u already, so I can solve for v and z. Once I know v, I can plug in v here, solve for x and y. So let's first of all rewrite this equation as a linear congruence. Let's first of all rewrite this equation as a linear congruence. I can write it as 7z congruent to u mod 2. 7z congruent to u mod 2. Then take 7 divided by 2, take remainder. 7 is more than 2. Take 7 divided by 2, take remainder. 7 divided by 2, remainder is 1. So 7z congruent to 1z. So 1z congruent to u mod 2. We know u is negative a minus 49t. U is negative a minus 49t. Let me plug in first. 7z congruent to negative a minus 49t mod 2. Plug in u first. U is negative a minus 49t. U is negative a minus 49t. Then take each number, divide by 2, take remainder. 7 divided by 2, remainder is 1. I get 1z. Negative a divided by 2. Take number a divided by 2. Don't worry about negative sign. Take number a divided by 2. Number a divided by 2, remainder is 0. Then take 49. Next, take 49 divided by 2. 49 divided by 2, remainder is 1. So 49t congruent to 1t. Negative 49t congruent to negative 1t mod 2. On the left side, 1z is the same as z. Negative 0 minus 1t is negative 1t here, mod 2. In general, we try to make the coefficient positive, so I can add 2 here. Negative 1 plus 2 is 1. So z congruent to 1t. 1t is the same as t mod 2. Z congruent to t mod 2. Z congruent to t mod 2. If I add 2 here, negative 1 plus 2 is 1. I get 1t. 1t is the same as t. So z congruent to t mod 2. Then write this as an equation. Write this as an equation. I can write z equal to t plus 2s. Z equal to t plus 2s, where s is an integer. S is an integer. Then here we know z. Once I know z, we know u already. Once I know z, I can plug in z and solve for v. We know u already. Once I know z, I can plug in z here, solve for v. So plug in 2v equal to 7z. Z is t plus 2s equal to u. U is negative a minus 49t. U is negative a minus 49t. Then solve for v. Solve for v. If I distribute 7, I have 7t plus 14s equal to negative a minus 49t. So 2v equal to negative a minus 56t minus 14s. Then divide both sides by 2. V equal to negative 4 minus 28t minus 7s. V equal to negative 4 minus 28t minus 7s. That's v. So we know v. Then I can plug in v here, solve for x and y. Here we know v. I can plug in v here, solve for x and y. Plug in v, solve for x and y. This equation is 4x plus 6y equal to 2v. The GCD of 4 and 6 is 2, and 2 divides 2v, so I can divide both sides by 2. I get 2x plus 3y equal to v. Then write this as a linear congruence. We know v already. Write this as a linear congruence. Solve for x and y. I can write it as 3y congruent to v. 3y congruent to v mod 2. 3y congruent to v mod 2. Then plug in v. V is negative 4 minus 28t minus 7s. Then, since 3 is more than 2, take 3 divided by 2, take remainder. 3 divided by 2, remainder is 1. I get 1y. 3y is congruent to 1y. Take negative 4 divided by 2, take remainder. Negative 4 divided by 2. Take 4 divided by 2, remainder is 0. Then take 28 divided by 2. 28 divided by 2, remainder is 0. 0 times t is 0. Then next, take 7 divided by 2. 7 divided by 2, remainder is 1. Mod 2. So we get 1y is the same as y, congruent to negative 1s mod 2. In general, we try to make a coefficient positive, so I can add 2 here. Negative 1 plus 2 is 1. So negative 1s is congruent to 1s. 1s is the same as s. Y congruent to s mod 2. Here we have y congruent to s mod 2. So I can write y as an equation. Y equal to s plus, write y as an equation. Y equal to s y equal to s plus 2, use a different letter, say r, where r is an integer. Then I know y. Once I know y, we know v already. Once I know y, and we know v already, I can plug in y and solve for x. Once I know y, I can plug in y. Since we know v already, I can solve an equation for x. So plug in, we have 2x plus 3y. Y is s plus 2r equal to v. V is negative 4 minus 28t minus 7s. Then simplify, solve for x. If I distribute 3, I get 3s plus 6r equal to 4, negative 4 minus 28t minus 7s. Then 2x equal to negative 4 minus 28t minus 10s minus 6r. If I divide both sides by 2, x is negative 2 minus 14t minus 5s minus 3r. So we have x, y, z, and w. We have s, y, z, w. So the final answer, let me put it here. The final answer, s equal to negative 2 minus 14t minus 5s minus 3r. Y equal to s plus 2r. Y equal to s plus 2r. S plus 2r. Try to line up the variables here. Y equal to s plus 2r. Z equal to t plus 2s. Z equal to t plus 2s. And w equal to 2 plus 6t. Where r, s, t are integers. Where r, s, t are integers. That's the solution to this linear Diophantine equation. That's the solution to this linear Diophantine equation. Now, we get some crazy answer here. How do we know this is correct? We get some crazy answer here. It looks crazy. How do we know this is correct? How do we know this is correct? If we plug in x, y, z, and w, we must get 50. If this answer is correct, when I plug in x, y, z, w, I must get 50. Let's check the answer. Let's just make sure. Let's check the answer. It looks crazy here. When we get something crazy, how do we know it's correct? Plug in x, y, z. If we get 50, then it must be correct. So 24 times x is negative 2 minus 14t minus 5s minus 3r plus 36 times y is s plus 2r plus 42 times z is t plus 2s plus 49 times w is 2 plus 6t. Let's simplify. If we get 50, then this answer is correct. If we get 50, this answer is correct. If we don't get 50 here, that means we made a mistake somewhere. We must go back and check the answer. For the final answer, all coefficients must be integers. All coefficients must be integer. And you must satisfy this equation. So let's check. Distribute 24. 24 times 2 is negative 48. 24 times 14. Let me use my calculator. In my calculator, I got 336. 24 times 5 is 120. 24 times 3 is 72. Plus 36 times S plus 36 times R. 36 times 2R is 72R. Plus 42T plus 42 times 2 is 84 plus 84S. 49 times 2 is 98 plus 49 times 6. Let me use my calculator. 49 times 6. In my calculator, I get 294. Then combine like terms. Negative 48 and positive 98 is 50. $42T plus 294T is 336T. Positive 336T cancels negative 336T. Then 36S plus 84S. That's 120S. Positive 120S cancels negative 120S. And negative 72R cancels positive 72R. The answer is 50. So this is the correct solution. This is the correct answer. It satisfies this equation. SYZW satisfies this equation. And they are all integers here. For all R, S, T, they are all integers. That's the solution to this linear Diophantine equation.